Imagine if we could plant water, and with the water planted, ensure that plants grow better, are supplied with water, that summer days become cooler, that it rains more, and that climate change could be mitigated. Wouldn't that be a tempting solution to many of the challenges and problems we have in agriculture and more broadly in our society? That's what this session is all about, and it's a surprisingly simple concept. Planting water, of course, isn't something we can directly do, but indirectly, it is quite feasible. If we look at the last few years, the predominant issues facing agriculture were the increasing summer drought, the associated increased air temperatures, and increasingly drier soils. The dry soils, as well as the increased soil temperatures, added immensely to the plant stress and drying soils, conditions that we here in Germany usually know from Mediterranean regions only. Interestingly, all these topics are related to one element, water, or rather the lack of water. So let's take a closer look at how it is all related. If we look at the precipitation patterns from a global perspective, then 100,000 cubic kilometers of precipitation fall on land surfaces. Where does this water, this precipitation, the rain, actually come from? Originally, about 70,000 cubic kilometers, or around 60%, come from the oceans, and 50,000 cubic kilometers, that's 40%, from land. This is probably a surprising finding for many, because we usually think that the precipitation in Western, Central, or Eastern Europe comes quite directly from the sea. However, this is actually not the case for many areas in the world, even in inner German regions, and then increasingly in the Eastern European countries. About 50% of the rain that comes down originates from land. This is a really important aspect. When we look again at these 50,000 cubic kilometers which originate from land and look to where the water is actually coming from, then we can see that 60 to 80% of it derives from vegetation. This means that 60 to 80% of what ultimately goes into the air as water vapor and then pours down again as precipitation on the land has its origin in vegetation. The rest, 20 to 40%, stems from water surfaces or to a smaller extent, bogs and soils. So what does that mean when we see such a picture, which may seem a bit exaggerated, but it is also widespread in Eastern Germany and Eastern European countries, as well in many other regions of the world? Keeping in mind that much of the precipitation that falls on our land stems from the land and above all from vegetation, it becomes clear that under these conditions of large areas with bare soil, the water for potential evaporation is not available for long periods of the year. In short, the natural small water cycle is interrupted when we operate in this way. This is not about pointing fingers at farmers who are doing something wrong. No, rather it is about changing the perspective and drawing attention to a topic that has hardly been dealt with so far, and which, according to everything we have been able to research in the meantime, offers many, many solutions. This means that if we develop appropriate measures from the knowledge gained, we are not only talking about a win-win solution, but rather about a win-win-win-win-win solution, because so many different extremely positive effects can be achieved through new approaches. Let's go back to the point of vegetation, which in turn produces evaporation. A large tree, as shown here in the picture, can transpire 400 liters of water on a warm summer day. The process of transpiration requires a considerable amount of energy. For 100 liters of water, the amount which such a tree transpires requires 70 kilowatt hours of energy. So for 400 liters that such a tree transpires, 280 kilowatt hours to turn liquid water into water vapor are required. That's a number which doesn't say much for most of us. Therefore, let us look at a comparison. These 280 kilowatt hours correspond to 8 air conditioning systems running for 24 hours, as shown here, and which are widely used, especially in southern countries. This is not only the energy required in the transpiration process, but also corresponds roughly to the cooling performance of trees or air conditioning systems. My daughter, when I started to work on this topic and while we were sitting outside in beer garden, asked the following question. Why does it feel warmer under a parasol in the beer garden than under the trees at the other end of the square, though we sit in the shade in both places? And yes, this is exactly the effect. The parasol only casts a shadow and prevents the sun's rays from hitting us directly, but it does not cool the ambient air. The tree, on the other side, not only provides shade, but also uses energy from the ambient air for the transpiration process and thus actively cools it, which is why it feels significantly cooler under a tree than under a sun canopy. Another picture can make these differences clear for us is the idea of going out on a hot summer day on a grain field or a plowed field or a mown meadow with 35 degrees Celsius ambient air temperature. On areas with little to no vegetation, the temperature feels closer to 45 degrees or more, with the soil temperatures reaching even higher numbers. But when we go into the neighboring forest, we find completely different temperatures, which are much lower and are more in the range of 25 degrees. On the other hand, this is the effect of the shadow cast by the trees. But above all, it is the result of the transpiration of the trees. That is the transpiration of water. And this is the cooling effect that vegetation can provide. It is important to know that vegetation is not only about transpiration in the sense of sweating. A tree is a truly three-dimensional object. If we measure a square meter of floor area on the ground under the tree and then pull it up through the tree, then the tree has a corresponding leaf surface for the square meter, which, depending on various factors, can be up to 25 square meters. Above each square meter of floor area is therefore up to 25 times the leaf surface, resulting in a very large surface area, which can help to transpire water and thus again contribute to cool the air temperature. 30 to 50% of the water vapor that goes into the air via the pumping of water from the ground to the trunk and over the branches into the leaves results from trees as they actively regulate the release of water via the stomata of the leaves. When it rains, part of the precipitation gets caught on the leaves, which can subsequently evaporate, in contrast to the active sweating of the trees, which is called transpiration. Evaporation makes up an important part of the entire evapotranspiration process. This so-called interception, like the active sweating of the tree, also accounts for 30 to 50% of the evapotranspiration capacity of a tree. Evaporation through the soil makes up for only 5 to 15%. If we now look at what this looks like on an area densely overgrown with vegetation such as a meadow or a forest, then we see that the soil absorbs about 5 to 10% of the energy of the incident solar radiation, which it later releases via long-wave heat radiation. A small part of 5 to 10% passes into the so-called sensible heat. That is what we can feel because the solar radiation warms the air around us. However, the vast majority of energy on a vegetated area, namely about 80 to 90%, is transformed into the so-called latent heat. This is the process where liquid water is transformed into water vapor, and thus energy from solar radiation and ambient air is consumed. So we do not feel a rise in temperature in the air. This water vapor and the energy stored in it is then transported by wind and buoyancy into higher air layers. If we now compare this with what happens in the field, then of course it looks quite different here. On a fallow field, about 10 to 15% of the incident solar energy heats up the soil. 70 to 80% passes into the sensible heat. This effect is easy to understand when we imagine going to a fallow field in the summer with 35 degrees air temperature, or in an even more extreme example, on a concrete surface where the temperature is then much warmer than just the 35 degrees. And this is exactly the effect of sensible heat, in which the solar radiation is converted into increased and directly perceptible air temperatures. Only a small part of 10 to 20%, depending on how much water, for example, is available in the soil, which is then available for the evaporation process, then passes into the latent heat, a big contrast to the 80 to 90% coming from vegetated area. These changes in the distribution of sensible and latent heat, as demonstrated by the two situations, come with crucial consequences. We can take a look at these different situations in order to make the process a little bit clearer. On the left side is a picture with some bare soil, a dandelion, and some grass. The top image is a normal shot, the low one is an infrared image. If we look at this little dandelion in the upper picture, we can see in the lower picture that it has a temperature of about 13 degrees, corresponding to the blue color. If we look at the bare soil, we see temperatures in the red area where we have 19 degrees. This means that between the small piece of bare soil and the covered soil is a temperature difference of 4, 5, or even 6 degrees. This is a small example illustrating how the response process is with sensible and latent heat. Now, let's look at the situation on a landscape level. At the top, we find a photograph with a small landscape section, and below it in the same area, we can see an infrared image. If we pick out this forest standing near the water here on the right, we find a temperature of 28.7 degrees Celsius. If we now go to the freshly mown meadow, a temperature of 39 degrees can be measured. This corresponds to a temperature difference to the forest of over 10 degrees. And if we look further to the left here, we find even higher temperatures of well over 40 degrees, with a winner being asphalt with a whole 49 degrees. That's a temperature difference of 20 degrees. This means we're turning back to the sensible and latent heat, where vegetation is grown and enough moisture is available, we find significantly lower air temperatures or sensible heat and high amounts of latent heat. And where there are open areas and bare soils, where there's no vegetation, we find significantly increased sensible heat and correspondingly reduced latent heat levels. Let's go back to the picture from before and see what the consequences are. What consequences result when different proportions of sensible and latent heat are generated from surfaces. So on the one hand, as I said, wherever water is being converted into water vapor, energy is needed for this process, which has the consequence that the ambient air temperature drops, which in terms of working natural processes on our environment and our climate corresponds to a positive effect. Of course, more moisture in the air potentially allows more clouds to form. Condensation, that is the conversion of water vapor into water, in turn releases the same amount of energy that was needed at the bottom for evapotranspiration. A small part of it can now diffuse into space and disappear. This is, in turn, is a positive effect if we see this from the point of view of climate change, because we also have to make sure that temperatures in the lower part of the atmosphere reduce as well as in the entire atmosphere. More clouds lead in the next step to more reflection, meaning if the sun's rays penetrate the atmosphere and meet the clouds there, which are very bright, then a part of it is reflected and correspondingly less light can penetrate deeper layers of the atmosphere. This ultimately leads to a lower production of heat. In terms of climate change, a positive effect. The Earth radiates long wave heat radiation back into space. With more clouds, this leads to an increased reflection of this heat radiation. So a small part of it is thrown back towards Earth, which is a negative effect in terms of climate change. The next very important aspect is more clouds lead to more precipitation. The small water cycle, small scale, more vertical movement of water between the Earth's surface and the atmosphere, in contrast to the large, more horizontal water cycle, which determines the transfer between ocean and land, can be activated and strengthened by these processes. More evaporation on the ground leads to more clouds, leading to more precipitation. In summary, this means that the processes that arise on the vegetated areas are not only positive from the point of view of reducing global warming, but also for agriculture. On the other hand, if we look at the picture on the right, the sharp increase in sensible heat leads to increased soil temperatures and increased temperature of the air layers close to the ground, so a clear negative effect. The significantly reduced evaporation leads to less cloud formation, because if no water evaporates, no clouds and thus no precipitation can form. And there is a certain tendency to high pressure layers. In short, the air here will expand more strongly due to warming, which will lead to a high pressure situation. High pressure areas block approaching low pressure areas, which bring the bad weather, in turn blocking humidity and possible precipitation from entering. The low pressure areas cannot push over high pressure areas and also cannot squeeze under these. The result in low pressure areas often releasing their precipitation beforehand or passing by in the periphery of high pressure areas, leading there to increased and sometimes torrential rainfalls. And of course, last point, the situation with bare or only slightly covered soil leads to reduced precipitation. When we contrast these two images, it is immediately clear what conditions we need and should create when we think of regenerative and resilient agriculture, but also when we think of mitigating climate change. In addition to the effect just explained, it is important to know that a theoretically black body emits proportional to the fourth power of its absolute temperature, heat power into the atmosphere. This so-called Stefan Boltzmann law demonstrates that the higher the temperature of a body, such as a field or asphalt, the disproportionately higher is the heat power radiated back into the atmosphere. We can see that the difference of the power radiated back between a temperature of 20 and 35 degrees is 95 watts per square meter, while it is 110 watts per square meter for the same temperature difference between 35 and 50 degrees Celsius. Here is an older picture from Australia with the so-called rabbit fence. That is the fence seen in the middle of the picture. On the left side, the natural vegetation has been preserved. On the right side, you can see the agriculture areas with little to no vegetation at this time of the year. And where do we find the clouds? On the left side, where there's vegetation. Water can transpire and clouds can form. Clouds prefer native vegetation, one could say. This is a nice example that clearly shows the different effects of land use and land cover. Let's look at the whole process on a geographically larger scale. Water vapor, clouds come from the oceans and drift onto the land. There, clouds form via the condensation process and precipitation takes place. This precipitation accumulates in the trees and in the soil and is then brought back into the air via evapotranspiration. That is the evaporation of water in the soil, of open water surfaces, and above all, as we've heard before, transpiration via vegetation, via the processes described earlier. There, the water condenses again, new clouds form, it can rain again, etc. This cycle is repeated again and again inland. If we look at these cycles and the large air and humidity currents globally, we see here on the map some of the very large so-called flying rivers that transport moisture from the ocean to the interior and recycle it again and again. According to the theory of the biotic pump, the forests are active designers of these air movements, among other things due to differences in air pressure caused by condensation. One can see from the example of South America, where we find the origin of the name flying rivers, since the phenomenon is most studied there, that moisture is drawn in from the ocean almost over the entire continent. But you can also see flying rivers in the States and in Europe, which goes from Western over Eastern Europe to East Asia. In fact, 80% of the precipitation that falls in Eastern China originates in Europe. This is what we see here on this map. The higher the values on the scale on the right side, the higher the precipitation recycling ratio. That is, the more precipitation consists of water, which previously poured down inland and repeatedly led to cloud formation via the known evapotranspiration process. The typical distances that moisture, which has evaporated over land, travels in the atmosphere before it falls back on land is in the order of 500 to 5,000 kilometers. The typical time scale ranges from 8 to 10 days. This explains why the moisture is recycled again and again via the westerly winds, which move from the Atlantic via Europe to Asia. Once precipitation takes place, it evapotranspirates again, leading to precipitation elsewhere and via Russia and Mongolia to Eastern China, which can result in high values of over 80% of the precipitation recycling ratio. But this rain, which falls in Eastern China, can of course only arrive there if this repetitive recycling is actively supported and fed by vegetation, and only to significant smaller parts of water bodies and fertile soils. Let's take a look at what happens when we disrupt this recycling process through activities that we know from all over the world, through, for example, deforestation and the resulting bare soils with significantly reduced evapotranspiration potential. Now we see that some things have changed in the hinterland, where less vegetation is leading to less evapotranspiration, which in turn leads to less cloud formation. This in turn results in reduced precipitation and further, even if there's forest there, reduced evapotranspiration. One can already imagine how the forest in the hinterland is doing with this reduced moisture flow. So this is the process of flying rivers with a constant recycling of the water. And if you interrupt it by deforestation or, for example, through vast fallow agricultural land, both lead to disturbance of the water cycle with correspondingly less precipitation and evapotranspiration inland. Here, for example, in a study from Indonesia, it is shown that over the deforested cleared areas, the temperature have risen by 10 degrees Celsius compared to the original forest. If we remember the pictures with the infrared images, where we were able to determine a temperature difference of 10 degrees between the forest supplied with water and dry soil, exactly this is the process of the disappearance of the forest. And likewise, 15% less precipitation was measured in these catchment areas. Serious changes that occurred there after removing a good part of the vegetation. Let's look at the issue of global warming. Here's the example of a graph I created for the United Nations Environment Programme, on which the measured temperature curves from the 4 established reference institutions worldwide can be seen. We can see a significant increase in the average global temperature of currently about 1.2 degrees Celsius since 1880, when the temperature measurements began compared to the average from 1818 to 1910. Various studies show that 18 to 40% of this global temperature increase can be explained by land use changes and the associated disruption of the water and associated energy cycle. So while for some time now the focus has been solely on CO2, which has indeed an important influence on climate change and whose emissions should be reduced and stopped as quickly as possible, one does not really hear anything in the current discussion about the contribution of these disturbed cycles, which also strongly influence the climate of the Earth. Let's look at the role of the different gases in the natural greenhouse effect. If the atmosphere with its various gases did not exist, the global temperature on Earth would be 33 degrees Celsius colder. Thanks to the atmosphere, these gases and their absorption capacity, we live with much more pleasant temperature conditions. The share of water and water vapor in this natural greenhouse effect is responsible for a whole 20.6 degrees, accounting for 66 to 85% of the total natural greenhouse effect. The effect of CO2 compared to water is only 7.2 degrees or 9 to 26%. Clearly, water is a major contributor to the natural greenhouse effect. This should give us food for thought when thinking about the impact land use changes, especially in recent decades, has on the water cycle. So far as I've heard, the argument has been that the human influence on the water vapor content in the atmosphere is negligibly small because, according to the argumentation, relatively small amounts of water vapor enter the atmosphere through human-induced industrial processes compared to the amounts that can be found there. And indeed, that's true. However, due to land use changes, we now have to talk about completely different dimensions. Research shows that due to reduced vegetation caused by deforestation and conversion to agricultural land in the period from 1950 to 2000, we have a reduction of evapotranspiration of 4 to 5%, which corresponds to 3,000 to 5,000 cubic kilometers of water, a gigantic amount. We also have a 7% increase in surface runoff water because the water that falls as rain on the land surface can no longer be completely absorbed by the soil and flows quickly into rivers and the sea. In addition, thanks to agriculturally implemented drainages and ditches, water is funneled directly via the fastest route towards the sea. Here again, the water is not being retained in the vegetation, in the soils, and in land depression and ponds. This faster flowing water is now no longer available for the flying rivers and the small water cycle. Over the same period, we also observe a 0.3 degrees Celsius increase in surface temperature due to these land use changes. Before, we were talking about a global temperature increase of 1.2 degrees. 0.3 degrees over the period of 1950 to 2000 looks like an important component of that increase. And this goes a bit further. Another study calculates that from 2000 to 2015, land use changes are responsible for a surface temperature increase of 0.23 degrees, where such changes happened. Of course, this has consequences. Over the period from 1700 to 1850, that is before the time of industrialization, the precipitation of the summer monsoon in India and Southeast Asia, China, fell by 20% due to changes in land use, above all, deforestation. This is an enormously high value if we look at this period of time, because until 1850, compared to what happened after 1900 and 1950, relatively little changed. After 1900 and 1950, the greatest land use changes worldwide began. So here again is an example of the consequences of the loss of natural vegetation on climatic factors, especially when you consider that at the time of the anthropogenic increase in greenhouse gases and aerosols was still negligible. Sometimes it is amazing how far-reaching the consequences of land use changes can be. Here's an example of such long-distance effects, or so-called teleconnections, between the Amazon and the northwest of the USA. Deforestation in the Amazon resulted in a 10 to 20% decrease in precipitation in the coastal areas of the northwestern US and the Sierra Nevada. Snow depth in the Sierra Nevada has decreased by up to 50%. Very amazing how far-reaching these long-distance effects can be. On the other hand, in addition to the flying rivers, there's also something like a flying drought. The Pantanal, a huge wetland landscape in southwestern Brazil, has been exposed to increasing drought since 2019, and as a result, has experienced more and more fires. These fires are now increasingly threatening this unique wetland biotope. The cause of this is, among other, especially human things, the warming of the Pacific Ocean southwest of the USA, where changes in the air currents are having an impact on the Pantanal. This again is an example of how complex the connections and effects are on our planet, and how land use changes, deforestation, and the establishment of far less moisture-giving agricultural crops can lead to large-scale climatic changes and local, regional, and global climate warming. The fact that land use changes are not only man-made, but also man-manageable is shown here by the example of the border region of Kazakhstan and China. Assuming that the climate and geological conditions in this area are comparable, there's a clear difference between these countries. On the right, the Chinese side, there is an area reasonably covered with vegetation, even if only for agricultural purposes. On the left, the region of Kazakhstan, there's hardly any greenery, and thus naturally a lack of potential for evaporation. More vegetation could be provided there through appropriate management. Another relatively well-known example is Haiti and the Dominican Republic. Differences in the economic situation, population density, and legislation led to a clearly visible difference in forest cover between these two countries. One consequence of deforestation in Haiti is soil erosion, which in some cases has reached serious proportions. Here's another photo that demonstrates the difference that can be attributed to different management practices. This picture again illustrates what happens when vegetation disappears and conditions are created under which the natural vegetation can hardly come back by itself, be due to the loss of valuable topsoil, an inappropriate pasture management, or a change in the microclimate that makes good growth difficult or impossible. Let us return to the topic of forests. The difference between a classically managed spruce forest very common in many areas of the world. And a diverse, resilient, deciduous, permanent forest can be seen, among other things, in the fact that the spruces in the example started here have only 75 liters of water per square meter at their disposal, while the mixed forest on the same subsoil and under the same conditions can fall back on 350 liters per square meter. Here, we find a huge difference in the amount of water that the soil on a certain forest can store and, of course, also release, or how trees can access it. The result being that in these two forest systems, there is a significantly different amount of water available in the summer months to carry out photosynthesis during this mostly drier time. This is all the more important in these times of climate change, where we are not talking about a rise in the global average temperature of 1.2 degrees, but have already reached 2 degrees and more in Germany during the growing season. Of course, this means that the trees need all the more the water during this period in order to carry out photosynthesis and grow healthily. If the water is not available, then of course they suffer, and in extreme cases, which are becoming increasingly common, die. Under these changed conditions, it is all the more important to encourage forest conversion in the direction of mixed forest and diverse permanent deciduous forest in order to be prepared for these changing conditions. The marked difference in water storage capacity is explained, among other things, by the different conditions in the forest as well as tree and root growth. The coniferous mulch litter found in spruce forest decomposes slowly and produces very acidic soils. Acidic soils in turn lead to an impoverished soil life. On the other hand, the foliage in deciduous forest leads to increased soil fertility because it can be decomposed relatively easily, increasing the population of living organisms, particularly microorganisms, such as bacteria and fungi, which are involved in decomposing organic matter and incorporating it into the soil. Deciduous forest soil also pleases the earthworms. The soil fertility enhances par excellence. The earthworms help increase the humus content, aerate the soils, increase water infiltration and storage capacity, and so on. The trees are happy about this and develop an increased network of fine roots, which further increases the soil fertility. Here we see the regenerative potential of the feeding and being fed nutrient cycle. There are important aspects and developments, especially when we consider that 42% of the land area of the EU 27 is covered with forest, and almost everywhere the monotonous plantations are suffering. A very exciting aspect is the direct and active involvement of trees in the formation of clouds and thus precipitation, and the associated acceleration or activation of the small water cycle. In addition to the importance of forests for energy fluxes and precipitation formation, large forests also appear to be biochemical reactors in which the biosphere and the atmosphere photochemistry generate nuclei for cloud precipitation formation, thereby maintaining the hydrological cycle. Indeed, trees produce VOCs, volatile organic compounds, and release microorganisms that live on leaves and become airborne during and after rainfall in forest ecosystems. In the atmosphere, they form an important part of cloud condensation and ice nuclei, which in turn affect cloud formation and precipitation. These biogenic aerosols can also help increase freezing temperatures by forming ice cores. Without these phenomenon, freezing would only occur at a cloud temperature of minus 15 degrees or colder. However, with the help of these ice nuclei, the process can be achieved at temperatures close to 0 degrees Celsius, allowing efficient cloud formation and making the formation of rain easier and more local. Let's move on to the issue of carbon dioxide. Since 1750, we have blown over 600 gigatons of carbon into the air through the burning of fossil fuels. Of this, about 245 gigatons have ended up permanently in the atmosphere. 170 gigatons have been absorbed by the oceans. The rest has been temporarily bound by vegetation. Now, as cited everywhere, we want to pull carbon out of the atmosphere to mitigate global warming and reach lower carbon dioxide concentrations. But there's a so-called gas pressure equilibrium between the atmosphere and the ocean. The carbon dioxide in a column of air above the water is in constant balance with the carbon dioxide bound in the water. This, by the way, is where the 170 gigatons in the oceans come from. If the atmosphere absorbs additional CO2 at any given time, the gas pressure equilibrium causes some of it to be absorbed in the oceans to restore the CO2 balance between the atmosphere and the water. But this also works the same way in the other direction. Let's say we successfully removed 45 gigatons of CO2 from the atmosphere. Then about 20 gigatons escape from the ocean to restore the balance. This means that over a longer period of time, we have to constantly remove almost 50% more CO2 from the atmosphere in order to reach the desired concentration of CO2 there. Our effort in this regard, currently not very ambitious or active, have to, in reality, be much higher, with the process being much more protracted than previously communicated. However, if we want to and must always look to nature for answers and search there for the best and most effective solutions. Here's a graph from the Mauna Loa measuring station in Hawaii, which has been measuring the CO2 concentration in the air since the 1950s. We see how the line keeps rising and has risen from 270 to 420 ppm in 2021. What's exciting now is this second red line that goes up and down gently, but very regularly. What is that? If we zoom in on such a cycle, as we see on the right side, we see that CO2 concentration rise in the first half of the year, then drop significantly in the summer month, and reach their lowest point in August, September, which makes a difference of about 7 ppm. What is the reason for this? Let's take a look at what is happening on a dynamic world map. The color red indicates high CO2 concentrations in the atmosphere. The color blue, low CO2 concentration. We start this animation in January and concentrate on the northern hemisphere. There we see how the color yellow is quickly joined by red over February into March and April. From May, and especially from June, the red and the highest CO2 concentrations disappear, the yellow dominates and then disappears more and more even in July. What is happening? This is more or less the natural CO2 Hoover called the photosynthesis process. The vegetation absorbs CO2 from the air, binds the carbon in the leaves, in the branches, in the trunk, and in the soil. With more vegetation, we could successfully pull more CO2 out of the atmosphere at these levels and bind it permanently. So working with nature and not against it seems to me to be the right approach here. Another danger, not only of cities, but also of open soils, especially if they occur on larger areas, is that they can generate these high pressure areas already mentioned at the beginning. This is shown here as an example on the diagram. The normal ambient temperature would be the 0-degree line. Above cities, open soils, or even dry grain fields, the air heats up fast, so the air rises and forms high pressure zones. These can disrupt the natural air currents by forcing incoming low pressure areas with moisture to push past the sides of the high pressure areas. This can lead to more precipitation in these regions as the air masses now have to squeeze past these high pressure areas, resulting in the extreme precipitation events that are becoming more frequent. A fundamental question is, how do we deal with water? In our current paradigm, here an example from the city, but agriculture has currently dominantly practiced, often mirrors it. Water is seen as a problem that needs to be disposed of and removed as quickly as possible. In the city, it is the drains where the water rushes into the hidden sewage system. On agricultural land, we have the drainages and ditches that channel the water towards the river and the sea as quickly and as efficiently as possible. This is the approach of the last decades. A very prominent example of how we deal with water is the Los Angeles River in the city of the same name. There's no longer any question of a river here, not only because there's only a small stream flowing, but because here, as in many other regions, the river has been straightened and walled in concrete so that the water ends up in the sea as quickly as possible. Without the possibility to be in a natural state, we take away the potential rivers have of providing habitat, increasing infiltration, and, for example, climate effectiveness. In the current paradigm, water is unfortunately not seen as a valuable resource that gives life and that we should treat with care. The use of water for agricultural production is also a growing problem in many regions. One issue is that fossil groundwater, which is formed over tens of thousands of years and non-renewable in our time dimensions, is being used in large quantities. But even younger groundwater supplies are emptied much faster than the time of their recharge. And then we are surprised by news like this. The Federal Office of Civil Protection warns of drinking water shortage in Germany. Falling groundwater and consumption in agriculture could endanger the supply of drinking water in the medium term. Where is the water supposed to come from that will replenish our groundwater reservoirs if we make sure that precipitation above and below ground flows onto and off our fields and ditches and streams, if houses, roads, and the increasing concrete surfaces of cities and industrial zones lead the water directly into the rivers and oceans? So if we live in such a paradigm as shown in the diagram on the left, where we see water as a problem that should be disposed of it as quickly as possible, where we let it run off superficially to the sewers, where groundwater reservoirs can hardly form again, and whose level is falling because too much is being taken out and too little is left to seep back into replenishing it. And despite this, we are surprised by such news. We need a new water paradigm, one that recognizes and values water and its natural cycle. The role that water plays for soils, vegetation, groundwater, climate, and also for us humans is immense. Therefore, we need to change our attitudes and infrastructure accordingly, including those in agriculture, in order to retain and encourage water to remain on the land for as long as possible. The trends are clear. We are facing a constant increase in extreme weather events, a decreasing circulation of water on land, a reduction in precipitation or negative distribution of precipitation patterns, reduced evapotranspiration and water infiltration into soils and groundwater. These developments indicate the disruption of and partial collapse of the small water cycle. A new water paradigm, a fundamentally new way of working with water, could halt and even reverse these disturbances we are seeing and lead to a renewal of natural patterns. Examples from various cities in Germany, Europe, and China, for example, show that this works well and can also be put into practice on a large scale. Here, even sponge cities are being developed with the goal of retaining maximal precipitation. Something similar can be planned and implemented on really large agricultural used areas. Contour farming and key lines are key words here, along with fixed rows of trees and meadow strips, which prevent water from surface runoff and instead hold water in the fine cracks of arable meadow soil or in swales, that is infiltration ditches, to give the water time to slowly disperse. Here's an example from Australia, where the founder of keyline design, P.A. Yeoman, helped a totally degraded area become fertile again. In the picture, we can see how the almost parallel to contour water retention practice results in wonderfully green areas on the pasture downslope, as the water can now slowly distribute and diffuse into these otherwise dry areas and supply the vegetation there. Here are several examples of implemented water retention practices that led to the regeneration of vegetation. And the top example, an area in Australia where landscape is brought back to life due to so-called check dams, small water retention basins. And in the lower picture, activities of the Rain for Climate initiative. We have built many such small water retention basins in Slovakia to delay and minimize direct water runoff and allow the water to infiltrate and fill the aquifers. Here's an example from the eco-village of Tamera in Portugal, where several lakes have been created in recent years. Instead of a steadily degrading landscape, as is the case in most areas of this region, nature has found its way back to full life thanks to the return of water. The eco-village inhabitants calculated that the amount of water they hold back from rapid runoff each year through these ponds and lakes is equivalent to the amount of IBC containers of 1,000 liters in size that, if lined up together, would reach from the eco-village that is in the southwest of Portugal all the way to Barcelona, a length of 1,300 kilometers. Not only in agriculture, but also in other sectors and across society as a whole, we are moving toward degrading and degenerative practices whereby natural resources are exploited and polluted. We must change this. The first step of action is to transition to a sustainable economy. However, preserving or sustaining is not enough. In times when we have disturbed the environment to such a large extent, we cannot be satisfied with merely preserving the status quo. We must think in greater steps towards a resource building and regenerative economy in order to rebuild and restore these natural resources, to give future generations a real future and nature the opportunity to rest and redevelop. That is why we need a paradigm shift now. What can this look like? Returning to our example in agriculture, what are appropriate practices? Here we see soil from two fields, one from the right and the other from the left side of a road. Same soil, same basic conditions. However, on the right side, the soil, on the left side, the soil is conventional cultivated, including plowing, monocropping, and pesticide use. On the right side, cultivated with methods from regenerative agriculture. The difference is clearly visible and self-explanatory. Humus contents are far different, and with them the water infiltration rate, water storage capacity, nutrient storage capacity, soil structure, etc. These two soils offer completely different environments for plant growth potential, among other things. Let us review what we have learned. We need to keep the soil covered as often as possible and disturb the soil as little as possible. One great way to achieve these goals is to transition from till to no-till farming methods. This helps cover and protect the soil for longer periods without disturbance, to name just a few advantages. This is only meant to show one possible solution, not to demonize a particular practice, while presenting the others as the ultimate solution. Instead of keeping open soil in the attempt to reach a short-lived good soil tilth for planting, resulting in the ultimate loss of soil quality, soil should also always be covered between the main crops by cover crops and green manures. These practices help promote soil life and increase soil fertility. By keeping the soil covered via living vegetation, we cool the climate and activate the small water cycle. We need to undersow crops to cover the soil completely. Of course, there are always the objections that this means competition for the main crop. But in fact, there are enough scientific studies as well as experiences from farmers on the various advantages of this method. However, in addition to courage, to knowledge and support with startup finance, such a regenerative transition requires a new economic system, one that not only calculates the annual balance on the basis of yields, but also takes into account the value and capital of soil health and other ecosystem services, so that they're ultimately rewarded by consumers and society. Lastly, it also means planting more trees and hedges. Agroforestry is the appropriate keyword for this, and fortunately, the knowledge and the movement are steadily growing. Internationally, we are seeing an increasing number of agroforestry projects and as well an increase in funding possibilities. The transition also means a different way of forest management. In place of spruce monocultures, we need diverse mixed deciduous forests, where the focus is on increasing soil fertility to help increase climate resilience. We need to retain more water, as for example, through contour farming or keyline design. We need to prevent water as well as soil from runoff. It means water retention even on larger areas. Here are pictures from the same region in Portugal. The effects of water infiltration and water availability are really astonishing. Planting water, that was our starting point. And our journey has revealed that many processes are interconnected. Ultimately, it is about returning to observe nature, to learn from it, and to develop nature-based solutions that work with rather than against it. Knowing this, many of the approaches described in this presentation can provide multiple solutions. This is not a win-win solution, but a win-win-win-win-win-win solution. Cooling the climate with more vegetation, reactivating small water cycles, building soils, making agriculture more resilient, and developing holistic systems. That is our goal. Thank you very much for your attention.